Hello everyone, welcome to Algebra 1A. On week 9 lesson, we're going to be going over slope and linear equations. Welcome, I'm glad you guys are here. For week 9, I want you guys to make sure you are getting into our online CK12 textbook. There are some good examples in there, some good reading for you. A lot of the questions I give you are based off that textbook, as well as the lessons. Make sure you're taking notes over this, as well as the textbook. Do the practice problems. Make sure you're getting all your resources you can, and then doing the weekly assignments using this video and the textbook as a resource. Let me know if you have any questions on any of the problems. I'd love to help work with you in my online classroom as well. For week 9, here's what we got going on. I want you to, if I give you a point on a graph or as an ordered pair, I want you to be able to find the slope formula. I want you to tell me what the slope of the line is. Again, you need 2 points to make a line, at least 2 points. The slope, we're going to talk about what that is today. Given a problem, I want you to be able to interpret the rate of change from the problem and then see the rate of change as the slope on the graph, and then actually use the slope, the rate of change to solve the problem. I'm going to give you a linear equation. I want you to rewrite it into slope-intercept form, and then make connections between the graph and the table form of the linear equation. If I give you a linear equation, I want you to be able to apply function notation to represent and solve linear equations. And finally, if I give you a problem, can you use linear equations, tables, and or graphs to figure out how to model and solve that problem? So lots going on. We're getting the linear patterns. I love that. The relationship between X and Y, graphing lines. Here we go. So here's a line on a graph. How can we describe the way the following line is changing? What are some words we could use? Well, if I go from left to right, I can think of it as an increasing line, right? I can think about points. I can see this point is when x is -6, I have a y value of -3. But here when x is -3, I have a y value of -1. And I can see that it's increasing this way if I actually label the points out. What other things can we do? We can say we have a positive slope. It's a steady increase, right? It's a nice, flat, even increase. It's not changing. All these things. So this is an example of a linear function or a linear change. It's a linear pattern in which we're increasing by the same amount over and over again. It makes a nice straight line. So to measure this amount of change, which is what I want to do, we need at least 2 points. But when we're figuring out, okay, this thing is growing, we have an x-axis, because this is a number line, right? And so I need to measure on my line between points how much is changing along my x-axis, but at the same time I have a y-axis. I have a number line over here, and the different points represent something on that number line as well. And so when I'm trying to model the change, I need to figure out, well, between this point and this point, how much change is happening on the x-axis between those 2 points. But I also need to change how much is changing along the y-axis between these 2 points, right? So we're going from there to there along the y-axis, but we're going from there to there along the x-axis. Slope is what we call the change in the y-axis. So we're tracking this variable y. We're looking at how that's changing. If I take the amount of change between 2 points on the y-axis and I divide it by the change in the x-axis, that is my rate of change, or that is what we call the slope. It's got my nice slope formula down there. Make sure you are looking at that. I would definitely write that down in your notebooks. The slope is the change in y divided by the change in x. And we have this nice formula here. I'll show you how it works. y2 minus y1, again, that's the difference between my two y values. x2 minus x1, that's the difference between my two x values. Okay, let's go back to our line here. What is the slope of the following line? Well, let's pick a couple points. and go through that here. So I'm going to use this point, which is an x value of 3, and it has a y value of 3. And I'm also going to use this point, which has an x value of 6 and a y value of 5. Okay, so if I use my slope formula, it says subtract your y values and then divide it by whatever you get when you subtract your x values. So let's think about what are my x and my y values then. Switch colors here. So this is an x value and that's a y value on my point. It says when x is 3, my y value is 3. And this is an x value and that is a y value. When x is 6, y is 5. I'm going to call this my first point, so x1, y1. I'm going to call this my second point, x2, y2. It doesn't matter which one you make, 2 or 1, it's just as long as you have a point. So now let's fill those in. So if I take my y2, which is 5, minus my value for y1, which is 3, we see that equals 2, right? Another way to think about that is from this point to this point, it increased by 2 along my y values. So we went from 3 up to 5. That was an increase of plus 2. Okay, but as my y values change, so do my x values change. It's a relationship between x and y, so let's figure that out now. x2 minus x1, my value for x2 was 6. My value for x1 is 3, so I'm going to put those in. So I have 6 minus 3 equals 3. So as my y values change by 2, my x values change by 3. They go from this point here, 3, increase all the way up to 6. Well, that's a change of plus 3. And if I put those together, if I change 2 in y per 3x, well, the rate is then 2/3, and that's my slope. We just calculated the slope of that line. Now, I only used these 2 points. What if I had used these 2 points? A different 2 points. Would I still get the same slope? Well, from -6 to right here, that's adding 3. And then if I add 3, I add 2. Yeah, it looks like it's still 2/3 of a slope. If I pick any 2 points, I'll get the same slope for a linear equation. Okay, let's find the slope now if I just have a series of points. So near I've got x, and as I put in these x values, 0, 1, 2, and 3, I get these function values. These are y values, but we're writing this out in function notation. If I wanted to list them out as a series of points, I could graph 0, 18, that's a point on my graph. 1, 13, that's a point in my graph. 2 and 8 is a point in my graph. And 3 and 3 is a point in my graph. And we can see the pattern is we're just subtracting 5 over and over again. So this is a nice linear pattern going on. We could graph these points, but we want to find the slope. So let's talk about how to find the slope. If you remember, I just need 2 points. So I'm going to use this point right here, and I'm going to use this point. I'm going to use the very end points. So same thing again, what's the difference in my y values? I have 18 minus 3. And we can see the difference there is 15. So we changed by 15 between those 2 points. But now let's do 0 minus 3. If I do 18 minus 3, I got to find out also the change in my x value. So 0 minus 3 is going to be -3. And the result, and I change it into my rate, my average rate of change, 15 divided by -3 equals -5. So my slope of this line is -5, which means I'm losing 5 in my y values per a change of 1 in my x values. So it's a negative slope. This is a decreasing line. Okay, here's a couple points. -3 and 18 and 9 and 22. What is the slope of the line? So this one I only have 2 points. I'm trying to figure out what is the slope of the line between those 2 points. Well, again, there's an x value and there's a y value. When x is -3, y is 18. And here's an x value and a y value. When x is 9, y is 22. I'm going to make this one my first point, x1, y1. I'm going to make this one my second point, x2, y2. And now I subtract my y values, 22 minus 18. And then when I do that, now I need to subtract my x values. So I got 9 minus -3. Notice how I had a negative x value here. And so I put it in parentheses and had 9 minus -3. A lot of times students will make mistakes by forgetting a negative or adding a negative or not being careful with the negatives. So this on the bottom turns into 9 plus 3. So I actually get a change of 12. 22 minus 18 is 4. And so the slope of the line, if I reduce this down, is 1/3. So that equals the slope. 2 ways to interpret this. When I increase along by 3 in x, on my x values, I increase 1 in y values. Or my rate is I increase 1/3 of a unit per a change in x, 1 of x. So there we go, slope of 1/3. If you wanted to graph it, you should see a change in 3 and then up 1. And it would be kind of a little bit more like a flat line. But that's what a slope of 1/3 would look like. It's still increasing, but it's not increasing by a lot. Okay, so we found a slope from a graph, we found a slope from a table, we found slope from just 2 points. Hopefully you guys get good at slope now. But let's look at a special case of slope, and that is a horizontal line. What is the slope of this line? Well, let's think about it by using a couple points, and then we'll kind of develop it. So I'm going to use this point. When x is -6, my y value is 3. Let's use this point. When x is 3, my y value is also 3. There's my x1 and y1. There's my x2 and y2. And so now let's use our slope formula. I subtract my y values, find the difference there. And at the same time, I subtract my x values. And I get 0/9. What does that mean? 0/9 reduces down to 0, so I have a slope of 0. Well, let's think about that here. I have a horizontal line, right? My x values are changing, my x values are changing, but I do not see any increase or any decrease. My y values stay exactly the same, so my slope is 0. There's no change. Interesting, huh? No change at all, flat line, no slope. And if I wanted to, since there's no slope, the equation for this line then is all the points have a y value that is equal to 3. That's the equation that you would use for that line right there. So all horizontal lines have a slope of 0. Well, now let's look at vertical lines. What's going on here? Let's do the same thing. Let's pick a couple points and let's see what we got for vertical lines. So I'm going to pick this point and this point. This point right here has an x value of 2 and a y value of 5. This point has an x value of 2 and a y value of -1. And let's calculate the slope using my slope formula. So subtract my y values, 5 minus -1. Subtract my x values, 2 minus 2, and I get 6/0. So 6/0. So what is going on there? Well, this is not equal to 0. If you take 6 divided by 0 and you put it in your calculator, you get an error. You cannot take a number and divide by 0. It is one of those laws of mathematics that you just cannot do. 0 does not fit into 6 a certain amount of times. I can't take a something and split it into 0 groups. What we call then is the slope is undefined. All vertical lines have an undefined slope. You cannot calculate it. You cannot think of it as slope. Another way to kind of show the absurdity of it would be like saying, well, what if we were measuring time and distance? This would be saying, okay, at 2 seconds, because there's a 2 right there, we were both -1 feet away. At 2 seconds, I was also 2 feet away. And at 2 seconds, I was 5 feet away. So if you were trying to keep track of time and distance, you would be in 3 different spots at the same time, according to our graph. In fact, an infinite amount of spots. So as time went on, you're all over the place. That's not really possible to think about, right? So it's undefined. All vertical lines have an undefined slope. Okay, let's kind of apply this now. We've done some abstract x's and y's, but I think slope makes more sense in the context of a problem. So here we go. We have a time as hours go by, 1 hour, 2 hour, 3 hour, 4 hour, 5 hours. We have a distance, and we want to find what is the rate of change at each interval for the truck driver. We got a truck driver, and we want to interpret what this graph is telling us. So let's think about starting at 0, 0. So at 0 hours, he's gone 0 miles. He's traveling along, traveling along, traveling along. And then at 2 hours, something seems to happen. So what is happening from 0 to 1? Well, he's going a distance, right? He goes 80 miles. So for part A, he goes 80 miles in 2 hours, right? Well, his rate of change then is 80 divided by 2, right? An increase in 80 divided by a change in x, 2 hours, equals 40 miles per hour. That's a slope. It's also my rate of change. It's also a no duh, that's his speed. He went 40 miles per hour, 80 miles in 2 hours. But there we go. We see slope is the same thing as average rate of change. Let's look at another one. Okay, what is he doing for part B? So during that stretch right here for 1 hour, he's not going anywhere, right? He's at the same distance. So he goes 0 miles in 1 hour. So his rate is 0 miles per hour. He's not a break, right? Get a truck stop, probably filling up with gas, filling up with coffee, chit-chatting a little bit, and then he's on the road again. So now we go over another hour for part C, and he goes 40 miles in 1 hour. So he goes that same speed again, 40 miles per hour, right? Then he stops again. For part D, he's got another slope. It's a horizontal line, so his slope is 0 miles per hour. And finally, he's ready to go back. He's dropped his stuff off. He's delivered it. He's got his bacon and eggs. He's ready to zip on back home, and he goes from 6 to 8. There's a change in 2 along my x values. So for part E, he goes 2 hours. And how many miles does he travel? Goes from 120 to 0. So negative 120 miles. So his rate of speed is now negative 60 miles per hour because he's going in the opposite direction. It's a decreasing slope. His distance away is decreasing. And he's going faster because he's excited to get home to see his dog, or he's excited because now his truck isn't so heavy. He's delivered all his goods. There you go. We can think about rate of change and slope as the same things when we're talking about linear equations. Hopefully this helps you guys see that. Okay, here's a kind of a subtle twist on that. What is his average rate of change for the first 4 hours? So now we're thinking about rate of change, but we're thinking about average rate of change. So a lot of things, the rate of change varies, but we want to know, well, on average, what is it? So now we're looking, okay, for the first 4 hours. So from 0 to 4, there's my change in x. We can see that at 4 hours, he ends up right here. Remember how many points we need to find the slope? We only need 2 points. So we have 0, 0. And after 4 hours, he is 120 miles away. There's my 2 points, right? 2 points are enough to find the slope of that line. So finding the slope of that line, subtract my y values, 120 minus 0. Subtract your x values, 40 minus 0. 120 divided by 40 is on average then, he went 30 miles per hour. Because he took a break on a little bit. So he went fast, took a break, went fast. So on average, during that span, he only went 30 miles per hour. So there's your idea of average rate of change as well. Okay, so far what do we know? Linear equations can be represented by graphs, tables, and equations. When we keep track of the change that we see in a linear equation, as x changes and as y changes, we want to quantify that. We call that number the slope. Lines can have a positive or a negative slope, depending on if they're increasing or decreasing. And slope is the same thing as a constant rate of change in a problem. Okay, so now I want to introduce the idea of slope-intercept form. We got this idea of slope. We've worked with this a little bit before. We've graphed things like this, and I really want to dig in more to understand this equation and how it works, because you're going to be working on this throughout this week in your Desmos activities, understanding the relationship between a linear representation in terms of an equation and then a linear representation involving a graph is huge. So what do we got here? Y equals mx plus b. Well, I got my variables, so there's my independent variable, right? Mathematically, we're showing relationships. So as that x value changes, whether it's time, whether it's miles, whether it's distance, whether it's shirts, whether it's coffee, whether it's nuts, it could be anything, right? X is something we're keeping track of, and y is the other variable. Y changes as x changes, and we want to try and find out the relationship between that. So there's my y, my dependent variable. We need to have x and y when we put together an equation. But what makes it linear now is this starting value, b, which is my y-intercept. That's why we call it slope-intercept form. And m is what's happening. It's my change. It's the slope of the line. So we start at a y-intercept, and then you can see we're adding some value over and over and over and over and over again. We're multiplying m by x to see how many times it increases by. Okay. So let's find the equation of some lines here. We got a, b, c, and d. And we're going to use this y equals mx plus b form and find the slopes and y-intercepts of those lines. So let's do A, B, C, and D. Okay, line A, right here, right? It's a negative line. It has a y-intercept of 5. And as a slope, if I look at it, it's going from 5 to 4 to 3 to 2 to 1. It changes over 1 and down 1. The slope is -1. So the equation of that line then is my y value is going to equal -1, because I'm changing -1 per x value, but I start at 5. There's the linear equation for that. And I can go into my Desmos calculator and I can graph that just to double check that it's looking right. Let's do B. So B is right here. It's got a y-intercept of 2. Crosses the y-axis at 2, so let's write that down. And for B, the slope is over 1. And it increases by 3. It goes up 3 squares, right? From 2 up to 5 as I change. So the slope on that one is 3. So the equation for b is y equals 3x. It's increasing by 3 over and over and over again, but we start at a y value of 2. Okay, let's keep trucking along. Going with the trucker theme. Line C, here we go. It's also a positive slope. It's got a y-intercept of -1. So it crosses the y-axis at -1. And it has a slope of over 1 up 2 units right there. And over 1 up 2 more. So the slope is 2. So my linear equation then is y. My y value is equal 2 times x minus 1. So we start off at -1, but then we add 2 over and over and over again. Okay, one more, example D. Let's do that one in black. D is way down here, kind of hiding. It's got a y-intercept of -3. And my slope is funny on this one, so it's going over 1, 2, 3, 4 units for x, so over 4, but then it goes down just 1. So my change in y, it decreases by 1 as x goes over 4. There's my slope, -1/4. So we got a fraction slope here. Putting it all together in the equation, I got y equals -1/4. So we go down slowly, times x minus 3. All right, there's some good examples of putting the right equation, matching it up with what I see on my graph in slope intercept form. We'll do some other forms of linear equations, but I really want you to get it solid in this form right here. Y equals mx plus b. Okay, let's play around a little bit more with that. Here you got an equation. Y equals -1/3 x minus 8. If I want to interpret that then, the y-intercept is -8. So if I was to go over and graph it, I'm going to go down 8. 1, 2, 3, 4, 5, 6, 7, 8. My line is going to go through that point right there. Now, let's look at what the slope is. The slope is this whole value in front of the x. It's being multiplied over and over again. So the slope is -1/3. Well, what that means is it's a decreasing line, right? It's a negative, and it's -1/3. So my change in x is on the bottom. My change is y on the top. So when we go over 3 units, 1, 2, 3. What happens when we go over 3 for x? We decrease my y values by 1. To go down 1, and I'll make another point right there. So if I was to graph this line, it's a decreasing linear function looking something like that. Crosses the y-axis at -8, and from there we over 3 down 1. We're decreasing. Okay, here's our last problem. We got a problem-solving thing here. We have a spring that if I stretch it out, has a length of 12 inches when I put a 2-pound weight on it. We can see that picture right here. So there's my spring, stretches out a little bit more. I put a weight on it, 2 pounds, and it's 12 inches long. The same spring has a length of 18 inches when I put 5 pounds, right? A little bit heavier up here. So it stretches out a little farther. Assuming it stretches out linearly, what is the length of the spring when no weights are attached? So this is right here. This is my question mark right there. Okay, there's a couple ways to think about this problem here. Any linear equation, if I want to try and use a linear equation, I need 2 points. I need 2 points to base off my line, right? If I have 2 points, I can find the slope. If I have 2 points, I can find an equation. If I have 2 points, I can do a whole lot of stuff with linear things. So let's try and figure out what we have for 2 points. Well, I have 2 situations right here. Looks like when I do 2 pounds, it stretches by 12 inches. But later on, when I do 5 pounds, it stretches by 18 inches. There's my 2 points. So let's write that down. 2 and 12, and then 5 and 18. I'm going to go ahead and graph those 2 points. So there's 1, 2, 5, 6, 7, 8, 9, 10, 11, 12. There's 12. So there's one of my points. And then 5 and 18, 13, 14, 15, 16, 17, 18. 18 would be right there. And 5 would be 2, 3, 4, 5, right there. So there's my 2 points representing my 2 situations. Now, one way to solve this problem is just to look at the graph and think, okay, this is a linear relationship. Let's just look on my graph and estimate, right about there. If I had to estimate that value, I'd say it's 1, 2, 3, 4, 5, 6, 7, 8, maybe 8.5. So from the graph, I'm going to estimate 8.5 inches long. All right, we just kind of thought through it one way there. So based on my graph and working backwards with 0 weight, which would be right here, that would start off at 8.5 inches long. Let's do it another way. Let's kind of use more of a table, right? We've been working with graphs, tables, and equations. So let's make an X and a Y chart here. And I'm going to go 0, 1, 2, 3, 4, 5. I think you'll kind of see why here in a second. Now I know when there's 2 pounds for X, I have a Y value of 12 pounds. So I'm going to put 12 in for Y. When I know I have 5 pounds for X, 18 was my value. And if I think about that, let's find the slope of the line right there. That's telling me as X increases by 3, my Y values increase by 6, go from 12 to 18, right? So in terms of a slope, that is, I add 6 inches to my spring when we added 3 pounds of weight. So my slope, 6 divided by 3, is 2. What that means is the spring stretches 2 inches per pound. That's my rate. And if we have that, we can work backwards then. I can go 12. Okay, if I add 1 more pound, my spring must be 14 inches. 2 pounds or 2 inches per pound. If I do another pound, that must be 16 inches. Another pound must be 18, adding 2 and 2. And I can work backwards. If I go backwards 1 pound, if I take off a pound, I'm going to lose 2 inches. It's going to go down to 10. If I go backwards 1 more, I'm going to lose 2 more inches, right? It's a linear pattern. It's the same thing over and over. And I'll go back down to 8. Now, let's compare. According to my table, when I have 0 pounds and work backwards, it should only be 8 inches long. But on my graph, we've got 8.5. So they're close, but I'm kind of thinking I messed up on my graph a little bit. My graph wasn't very precise. I'm feeling really precise about my slope and what I did over here algebraically in my table. So the length of the spring should be 8 inches. But my graph kind of supports that. I got pretty close to 8 inches on my graph. I just didn't draw a very good line. And then finally, if I want to put this all together in a nice linear equation, I've got my slope, 2 inches per pound, that's how much it increases, and I've got my y-intercept. So the equation for this line would be the spring is stretched, that's my y value, 2 inches per pound times however many pounds I add, but that spring starts off being 8 inches long. And there is an equation that fits what we graphed, and it fits our table, and it fits this whole scenario. It's a great problem. Hopefully you followed all that. Again, what did I need? I needed 2 points to start off this whole process with. Okay, how was that? Week 9. We did lots of graphing. We did lots of points. We found slopes, whether it's a table, whether it's a graph, whether it's points, you can find the slope of the line now. And then if I give you a problem, you can use slopes, you can use graphs, you can use a table, you can use an equation, you can use all these tools now to help you solve and think through all sorts of problems. Again, hopefully you have fun working on the assignments for this week, and let me know if you have any questions.